This is the Linear Algebra Lectures video series. You can find more information about this video as well as a link to the written textbook in the description below. Stick around to the end of the video to learn more about this video series and the associated teaching and learning tools I've created for it. Lecture 13, Applications to Chemistry. Our objective for this lecture is to use linear algebra to balance chemical equations. In chemical reactions, chemicals are combined to produce other chemicals. So for example, this chemical equation represents the reaction when propane, C3H8, burns with oxygen, O2, to produce water, H2O, and carbon dioxide, CO2. Atoms are neither created nor destroyed by this reaction, just rearranged. So for example, if there are 10 million carbon atoms before the reaction, there will still be 10 million carbon atoms after the reaction. Our goal is to find coefficients for the chemical equation to represent the ratios of the various chemicals before and after the reaction. Don't worry if you don't know any chemistry, we're just going to be using our linear algebra tools to solve these application problems. So to set up the problem, we're going to put variables in front of each compound. So here we have variables x1 through x4, and we're looking for integer values of those variables so that the number of atoms of each element on the left-hand side equals the number of atoms of that element on the right-hand side. We're going to have one equation for each different element that appears in the equation. So in this equation, we have three elements: carbon, C, hydrogen, H, and oxygen, O. So we have one equation for each element. To find our carbon equation, we find the C's on both sides of the arrow, and on the left we see that we have three carbon atoms in the compound C3H8, but that's the only C that we have on the left-hand side, so the left-hand side of our equation is 3x1. On the right-hand side, we just have a single C with coefficient x4, and so the right-hand side of our equation that we're building is 1x4. For our hydrogen equation, on the left we have 8x1, and on the right we have 2x3. And for oxygen, we see that O appears in two different places on the right-hand side. So our left-hand side of our equation is 2x2, and the right-hand side is 1x3 plus 2x4. Now that we have our equations, we next need to put them in standard form by subtracting all the variables to the left-hand side. Once we do that, we get a homogeneous system of equations that you can see here. The next step is to set up the augmented matrix, and then we row reduce that matrix. And once we have our row-reduced matrix, we rewrite each row as an equation, and then solve those equations for those basic variables to get our general solution. Now, ordinarily, we would be done at this point, but what we're looking for is a specific solution to this system of equations. We want the solution that has the smallest possible positive integer coefficients. And so we're looking for the value of x4 that makes all of our variables be integers, and we want the variables to be as small as possible. So because we've got coefficients of 1/3, 5/3, and 4/3 in our general solution, we should hopefully see that the solution that we're looking for is x4 equals 3. Once we set x4 equals 3, that gives us the values of our variables, which lets us set up our balanced equation. And remember that these coefficients represent ratios. So for example, if we had 10 million molecules of propane, that's C3H8, then the 4 on the right-hand side of our balanced equation in front of water, H2O, would tell us that those 10 million propane molecules before the reaction correspond to 40 million water molecules after the reaction. Let's work through another example. So again, we don't need to know the names of the chemicals or what this all represents. We don't need to know the names of the elements. We just need to recognize that in this equation, our elements are N, H, Cl, Ag, and O. There's 4 compounds, which means we're going to have 4 variables. So you put a variable in front of each compound. And there's 5 elements, which means we're going to have 5 equations. As before, for each of those elements, you find the places where those elements occur on both the left and the right-hand sides of our equation and set up corresponding mathematical equations. So for n, our equation is 1x1 plus 1x2 equals 2x3. Notice that in the compound on the right, the n appears twice, so we've got 2 n's in that compound. For h, our equation is 4x1 equals 4x3. For Cl, the equation is 1x1 equals 1x4. For Ag, it's 1x2 equals 1x4. And for O, it's 3x2 equals 3x3. So we take those equations, rewrite them in standard form by subtracting the variables over to the left, set up our augmented matrix, row reduce that augmented matrix, and then write the general solution. And again, in this case, we're looking for the smallest possible positive integer value for our free variable that makes all of the variables be integers. In this case, since we don't have any fractional coefficients, we can use x4 equals 1. And that gives us our balanced equation. So when you're working through these kinds of problems, here are a few things that are important to keep in mind. You're going to have one equation for each element that appears in the equation. And again, you don't need to know the names of the elements or anything like that. All of the element symbols are either going to be capital letters, one single capital letter, or a capital letter followed by a lowercase letter. You're also going to have one variable for each compound that appears in the equation. So you're going to put those in, and those are going to be the variables that appear in your system of equations. The system will be homogeneous, which means that there's always going to be solutions, and you're looking for the specific solution that makes all of the variables equal positive integers that are as small as possible. So look for fractional coefficients in your general solution and find the smallest positive integer that cancels out all the denominators of those fractions to make all of these solutions be positive integers. Thanks for watching this video lecture. You can find links to the other videos in this series and to the written textbook in the description below. If you're an instructor, you can contact me for more information about the over 300 online linear algebra homework problems that I've created for the free My Open Math platform.